Picture this. You're an astronaut aboard the International Space Station, floating 254 miles above Earth's blue marble. Today's mission? Routine maintenance on the ISS's exterior hull. Your EMU, Extravehicular Mobility Unit, spacesuit, a $500 million piece of engineering, protects you from space's deadly vacuum. 2 safety tethers connect you to the station, your lifelines in the cosmic void. But then, the unthinkable happens. A micrometeorite impact, metal fatigue, or equipment malfunction. It doesn't matter what caused it. Both tethers snap simultaneously, and suddenly you're drifting away from humanity's orbital outpost. For the first few seconds, you're still in ISS's orbital path, but your tiny velocity difference is about to write your death sentence. This is where physics becomes your executioner. During the initial 10 to 15 minutes, you're not actually falling yet. In orbital mechanics, small velocity changes gradually alter your trajectory. The ISS travels at 17,150 miles per hour, and you've separated with just a few feet per second difference. This seemingly insignificant change slowly pulls your elliptical orbit's lowest point, the perigee, toward Earth's upper atmosphere. Your EMU's computer systems are frantically calculating your situation through GPS signals and internal sensors. The primary life support system, PLSS backpack, continues its normal operation. Oxygen flowing at 6 cubic feet per minute, carbon dioxide scrubbers working efficiently, cooling water circulating through your liquid cooling and ventilation garment. Oxygen levels read normal. You've got 6 to 8 hours of life support, more than enough for what's coming. But psychological terror begins immediately. Through your helmet's gold-tinted visor, you watch the ISS shrinking away. The massive solar arrays that once dominated your view become tiny glints of reflected sunlight. Radio contact with Mission Control Houston becomes intermittent as you drift beyond communication range. The last transmission you hear, "Houston, we have lost telemetry from EVA-1. Within 30 minutes, your orbit begins decaying to around 236 miles altitude. At this height, atmospheric effects are minimal but present. You're in the thermosphere, where air molecules are so sparse that you can't yet feel atmospheric drag. However, your suit's external temperature sensors detect the first signs of molecular interaction, a temperature rise of just 2 to 3 degrees Fahrenheit. Your suit's heads-up display shows telemetry data, decreasing altitude, stable life support, rising skin temperature on the suit's exterior. The EMU wasn't designed for atmospheric reentry. NASA engineers calculated every possible scenario for EVA operations, but a complete orbital decay was considered so unlikely that no contingencies exist. The silence is overwhelming. In space, there's no air to carry sound waves. Your only audio is the mechanical hum of life support systems, your own breathing, and the occasional crackle of radio static as you pass through ionospheric interference. You're truly alone in a way that no human in history has ever experienced, falling toward Earth with no possibility of rescue. After 45 to 60 minutes of orbital decay, you cross the 62-mile mark, the Kármán line. This invisible boundary officially separates space from atmosphere. You're technically in Earth's atmosphere now, but it's still too thin to breathe. The atmospheric density here is 1/10,000,000th that of sea level, essentially still a vacuum by Earth standards. At 50 to 53 miles altitude, you enter the mesosphere. Here, you first feel real atmospheric friction. Individual air molecules, though sparse, begin striking your spacesuit at tremendous velocity. Each impact transfers kinetic energy into thermal energy. Your spacesuit's outer layers begin heating up from a comfortable 35 degrees Fahrenheit to 85 degrees Fahrenheit within minutes. The EMU's thermal control system activates its warming protocols. Ironically, the wrong response. The thermal meteoroid garment, designed to protect against space debris and radiation, now faces a new threat: atmospheric heating. The multi-layer insulation that kept you warm in space's frigid vacuum now traps heat that has nowhere to escape. Your descent velocity is now approximately 670 to 750 miles per hour. The mathematics of atmospheric physics begin working against you. Kinetic energy equals 1/2 mass times velocity squared. As your speed increases, the energy released during atmospheric interaction grows exponentially. Inside your helmet, the first signs of trouble appear. The anti-fog coating on your visor works perfectly in vacuum conditions, but wasn't tested for prolonged atmospheric entry. Condensation begins forming at the edges as your suit's internal temperature regulation struggles with the changing thermal environment. You're still conscious and aware, watching Earth grow larger through your visor. The blue marble that astronauts describe with poetry and wonder now appears as your destination and your grave. Continental outlines become visible, cloud formations show detail, and you can distinguish between land and ocean masses. The psychological impact is overwhelming. You have roughly 30 to 40 minutes of conscious thought remaining before heat and system failures incapacitate you. There's enough time to contemplate your situation, to think about loved ones, to consider how your name will be remembered in space exploration history. You're about to become the first human to die from uncontrolled atmospheric re-entry while conscious. At 43 miles altitude, you penetrate the stratosphere. Here, the ozone layer creates a denser atmospheric environment, and friction becomes serious business. Your suit's exterior surfaces reach 390 to 570 degrees Fahrenheit within minutes. The white outer fabric of your EMU begins changing color, first to brown, then to black as thermal degradation accelerates. The EMU's thermal management system is failing catastrophically. The primary life support system's cooling loop, designed to remove body heat in vacuum conditions, cannot handle atmospheric heating. Water in the cooling garment reaches uncomfortable temperatures. The liquid cooling and ventilation garment that normally keeps you comfortable at 65 to 75 degrees Fahrenheit internally now approaches 90 degrees Fahrenheit. Multiple system alarms activate inside your helmet. Warning lights flash red across your heads-up display. Thermal overload, cooling system failure, suit pressure anomaly. The computer's synthetic voice repeats warnings that no astronaut training ever prepared you for. Atmospheric entry detected. No contingency protocol available. Inside your helmet, warning lights flash. Your suit's cooling system is overwhelmed. Body temperature starts rising as the EMU becomes an oven rather than protection. Sweat fogs your visor despite the anti-fog coating, creating a bizarre situation where you're simultaneously overheating and watching ice crystals form on your helmet's exterior surface as you pass through the stratosphere's ultra-cold regions. The EMU's pressure regulation system faces unprecedented challenges. Designed for vacuum conditions, it now must manage rapidly changing external pressures as you descend through varying atmospheric densities. Pressure relief valves, meant to prevent overpressurization, begin venting atmosphere in microsecond bursts. At this point, you're falling at roughly 1,100 miles per hour, but atmospheric density is increasing exponentially. The physics equation for atmospheric drag, 1/2 RHO v squared CdA, shows that drag force increases with the square of velocity and linearly with air density. Both factors are working against you now. Your spacesuit's communications system picks up radio traffic from commercial aircraft 30 miles below. Pilot voices discussing weather conditions and flight paths create a surreal juxtaposition. Normal human activity continuing below while you plummet toward them in a failing spacesuit, invisible to air traffic control radar due to your small radar cross-section. Entering the troposphere at 6 to 7 miles altitude, you encounter the densest part of Earth's atmosphere. Your velocity exceeds the speed of sound. You've become a human sonic boom, traveling at Mach 1.4. The shockwave forms around your EMU, creating a plasma field of superheated air that glows visibly in the electromagnetic spectrum. Temperature readings on your suit's exterior exceed 2,000 degrees Fahrenheit, hot enough to melt copper. The EMU's outer materials, orthofabric, beta cloth, and mylar thermal layers, designed to protect against micrometeoroids and radiation, begin ablating. Pieces of your spacesuit's thermal protection start burning away, creating a debris trail behind you visible to anyone who might be watching from the ground. The ablation process follows known physics. As materials reach their vaporization point, they carry away thermal energy, providing some protection for inner layers. However, the EMU was never designed for this thermal environment. Each layer failure exposes the next layer to increasingly impossible conditions. Your internal temperature is climbing dangerously beyond human survival limits. The cooling system failed minutes ago. Heat stroke symptoms begin manifesting. Confusion, nausea, rapid heartbeat approaching 150 beats per minute. Your core body temperature reaches 104 degrees Fahrenheit, then 106 degrees Fahrenheit. At 108 degrees Fahrenheit, cellular damage becomes irreversible. Your body is cooking inside what was supposed to be humanity's most advanced protective equipment. Consciousness begins fading in and out. The medical term is hyperthermia-induced altered mental status. Your brain, requiring precise temperature regulation to function, begins shutting down non-essential processes. Vision tunnels. Hearing becomes muffled, and coherent thought processes deteriorate. Through your fogging visor, you can now see individual buildings, roads, and vehicles. The ground that seemed impossibly distant an hour ago now fills your entire field of vision. Lakes and rivers appear as distinct geographical features rather than abstract blue shapes. If you're falling over populated areas, some people below might notice a bright streak across the sky, similar to a meteor but following a different trajectory than natural space objects. Emergency services might receive calls about a fireball or aircraft in distress, never imagining they're witnessing history's first astronaut atmospheric entry. At 2 to 3 miles altitude, atmospheric density becomes so great that drag forces finally balance gravitational acceleration. You reach terminal velocity, approximately 200 miles per hour for a person in a spacesuit configuration. This represents the maximum speed achievable when gravitational force equals atmospheric resistance. The mathematics are precise and unforgiving. Your drag coefficient in the EMU configuration is approximately 1.3, your frontal area roughly 6 square feet, and your total mass including suit approaches 460 pounds. Using the terminal velocity equation, Vt equals the square root of 2 mg divided by rho a cd. The result is 200 miles per hour, fast enough to guarantee instantaneous death upon impact. But by now, the EMU is no longer functioning as intended. The pressure suit has likely been compromised by thermal damage. Multiple layers have failed, seals have degraded, and the life support system has shut down. If you're still conscious, which is unlikely given the thermal stress and system failures, you're experiencing decompression effects, severe thermal injury, and hypoxia simultaneously. Your suit's remaining intact systems show catastrophic readings: internal pressure dropping, oxygen flow ceased, cooling system offline, communications dead. The primary life support system that kept you alive for hours in space's vacuum has become useless baggage attached to your dying body. The EMU's hard upper torso, designed to maintain structural integrity in vacuum, now experiences stress loads never anticipated by NASA engineers. Thermal expansion and contraction, combined with aerodynamic forces, create metal fatigue in aluminum components designed for space's static environment. Weather conditions below affect your final approach. Wind shear at different altitudes alters your trajectory slightly. Temperature inversions create pockets of different air density, causing momentary acceleration or deceleration. These minor variations don't change the ultimate outcome, but affect exactly where your impact occurs. If you're falling during daylight hours, your blazing descent might be visible to aircraft pilots, hikers, or anyone who happens to look up at the right moment. Some might mistake you for a small aircraft in distress, others for an unusual meteorite. None would guess they're witnessing the final moments of a human being who left Earth's surface as a symbol of human achievement and exploration. The mathematics are simple and brutal. A 180-pound astronaut in a 280-pound spacesuit hits the ground with kinetic energy equivalent to a small bomb, roughly 2.8 million foot-pounds of force, or approximately 3,800 kilojoules of energy released in milliseconds. Ground impact occurs at terminal velocity after approximately 12 to 15 minutes of atmospheric flight time. The total journey from ISS separation to ground contact takes roughly 90 minutes to 2 hours, depending on initial orbital parameters. The human body can survive impacts of about 50 Gs for milliseconds. Ground impact from terminal velocity generates forces exceeding 200 Gs, lasting several milliseconds. Every bone fractures simultaneously. Organs experience liquefaction. Death is instantaneous. The EMU, despite thermal damage, might partially protect against impact, but only enough to keep some biological material intact for identification purposes.